Okay, this is the Year 2 book, Chapter 2, and it's question 22 on functions. And in this case, we have a function containing powers of x and numbers, and also it contains a log function. And we have to use calculus to find the coordinates of the points A and B, the stationary points where the gradient is 0. Okay, now we therefore need to differentiate, and you may not know how to differentiate the function log x, but we're going to look at this by considering the gradient of the function e to the x, which you do know about. So let's just consider first of all the graphs of y equals e to the x and y equals log x and the relationship between them. Okay, so I've done this little illustration here first of all. So there we have the graphs of y equals e to the x here in green. Okay, so you should be familiar with the shape of that. And if you reflect it in the line y equals x, which is the blue line, okay, you should know that that gives you the inverse function of e to the x, which of course is the natural log of x. Okay, so those are illustrated there. Now, hopefully you can recall this very important fact. If I took a piece of line, let's say at the point when y equals 2, okay, if I just draw that straight line on there, just to illustrate there. So that piece of line I've just drawn, okay, when y equals 2, has a gradient of 2, because that's one of the fundamental properties of e to the x, that when you differentiate e to the x, you get e to the x. So here y is 3, the gradient would be 3. Here y is 1, and the gradient of that part of the curve would be 1, you see. Now, if the gradient of that piece of black line there is 2, then if you reflect that piece of black line there in the line y equals x, it would be here, and it would have a gradient of a half. Okay, so that has a gradient of 2, that has a gradient of a half. Okay, and because the y coordinate of this becomes the x coordinate of this when you take the inverse function, then I can see that the gradient here is 1 over x, because it was 1 over the y coordinate of this, which is 1 over x. So the gradient of the function y equals log x is actually 1 over x. Okay, and that is the differential of the function log x, 1 over x. So using that information now, I'm going to differentiate this whole thing here. Okay, so for part A, I'm going to write that f dashed of x, that's the gradient function, okay, is equal to, well, hopefully you know that the x squared becomes 2x, the minus 7x just becomes minus 7, and the 5 log x is 5 lots of 1 over x, which is 5 over x. Okay, and then the plus 8 becomes 0. Now we also know that the gradient function has to equal 0 at a stationary point at A and B. So if that's true and that's equal to 0, then if we multiply everything by x, we get a quadratic that we're going to solve. We get 2x squared minus 7x plus 5 equaling 0. Okay, that factorizes nicely to give us 2x minus 5 and x plus minus 1 x minus 1. Okay, both negatives there to give us the plus 5. And that gives us, therefore, that x equals 5 over 2 or x equals 1. Okay, they're the two values of x, which are these two coordinates a and b. Well, you can see which one is which. This is the 1 and this is the 5 over 2 here. So what are the actual y coordinates of those points? Well, let's do the 1 first, because that's quite easy. So when x equals 1, okay, f of x is equal to, well, we've just got to put 1 in here. It's going to be 1 squared minus 7 plus 5 lots of the log of 1, which is 0, okay, plus 8. Okay, and if you work that out, that gives you negative 6 plus 8, which is equal to 2. Okay, so that implies that the point A has coordinates of 1, 2. Okay, so that's this point here. Now, what about point B? Well, let's just work that out. So when x equals 5 over 2, okay, f of x rather, not f dashed of x, f of x, the original function, well, it's going to be 5 over 2 squared, which is 25 over 4. Okay, we've got to subtract from that 7 lots of 5 over 2, which is 35 over 2. Okay, we've got to add to that 5 lots of the log of 5 over 2. Okay, and we've also got to do something with the 8. We've got to add 8 on. Okay, and if we put all that into the calculator or simplify it, we get 5 log 5 over 2. We could simplify that or write it in other ways, but we'll leave it like that as a log, and we take away from that negative 13 quarters. Okay, that is the y coordinate of the point B. Okay, and it works out, it's about 1.33 on the calculator. Okay, but leave it like that in natural form, and so that means that the point B is equal to 5 over 2, comma, and then it's 5 log 5 over 2, okay, minus 13 quarters. So that's the coordinates of the point B. Now, and that's the answer to part A. Now we've got to sketch the curve with this equation. Now I've cheated here because using the tablet to do a sketch is really difficult, so I've done it already here and I'll drag that in, but you would do it on your graphic calculator. And basically you've taken the original function, you've translated it 2 places to the right, okay, and you've reflected it in the x-axis and multiplied everything by 3. In other words, the points A and B are 3 times further away from the x-axis, but on the other side because of the minus 3. So basically it's this, and I'll bring this in and we can have a look. Here it is. Okay, so it's like this. Let me just move this out the way that we've used earlier. If I just take this out of the way, okay, and just remove that stuff. Okay, then we've got a bit more space. Okay, so that is the sketch of our function. Okay, so you can see that the point A has been moved down to here. The point B is now here. Okay, 3 times further away from the x-axis, but also the whole thing has been shifted 2 places to the right. Now, you should know that this line would have an asymptote on the y-axis, okay, because x has to be greater than 0. Okay, that's one of the restrictions in the domain, because you can't take the log of 0 or a negative number. All right, and as x gets very, very small, log x becomes a very large negative number. So as x approaches 0, log x approaches negative infinity. Okay, so that is an asymptote, and that asymptote is effectively now moved to the line x equals 2. Okay, so I could just mark that in, and I'll do that here. So that's the line x equals 2, which is now an asymptote. Okay, I'll just draw that in there like that. Okay, and usually on an asymptote we tend to show it as a broken line, so I can just quickly illustrate that for you like that. Okay, now the next thing we need to do is identify these points A and B. Okay, so I've answered question B here really. I'm going to be doing C at the same time, but I'll just label this question B. Okay, now what I've got to do is I've got to say, well, this coordinate has moved along 2 units to the right, so it was originally the point 1, 2, so it's now going to be the point 3, okay, because it's 1 plus 2, and this was at plus 2, so it must now be at negative 6, because it's 3 times further away and on the other side of the x-axis. So the point A has moved to there. That's quite easy. This one, well, you apply the same rules. So it was 5 over 2, which is 2.5. So it's gone another 2.5. So it's now at 4.5, or 9 over 2. So that's its x coordinate. So I'll start over here because it's going to take up quite a lot of space. 9 over 2. Okay, that's the x coordinate. Okay, now the y coordinate is going to be this thing here multiplied by 3, but changed into a negative. So if I take the 13 over 4, that becomes 39 over 4, and it becomes a positive, so I could put it at the front. Okay, 39 over 4. And what was positive was the 5 log 5 over 2, which now becomes negative 15. Okay, log 5 over 2. Okay, lots of brackets here because you really do need the brackets around the log argument. Okay, like that. But then, of course, you need the closing bracket for the coordinates as well. So writing it in natural form makes it a little bit cumbersome to write down, but that's it. Okay, so it's 39 quarters minus 15 lots of log 5 over 2, and that's the coordinates of the new position for the point B, and that's A there. Okay, and it just says find the coordinates of the stationary points of that. Without proof, I just had to state which point is a maximum and which point is a minimum. Okay, well, it's from the graph, and it's pretty obvious that that B is now a maximum. If I call this B dash, okay, and this A dash, because they're the reflected points, okay, or the transformed points, then I can just say B dash, okay, is max and A dash is a min. Okay, and that pretty well answers the question. Okay.